we'll look into the next problem. 5.28. The data in table have been obtained on the decomposition of gaseous reactant A in a constant volume batch reactor at 100 degrees Celsius. Stoichiometry is 2A gives R plus S. Okay, gaseous reactant is there, 2A gives R plus S, so 2 moles giving 2 moles. What size of plug flow reactor in liters operating at 100 degrees Celsius and 1 atmosphere can treat 100 moles of A per hour in a feed consisting of 20% inerts to obtain 95% conversion? Now here stoichiometry is 2A gives R plus S, 2 moles giving 2 moles, so number of moles are constant. But if pure A is used, then epsilon is 0. 20% inerts are there, so you have to again calculate epsilon and check. It may be 0. You have to check. You have to just cross check with the number of inerts. Okay. So 2A gives 0.8 plus 2, 80% of A, 20% of inerts. What you get is 20% inerts as it is. 2 moles of A give 1 mole of R, 1 mole of S. So 0.8 will give you 0.4 and 0.4. So 1 minus 1, this is 0. So we have verified. Ca0 value. Mole fraction is 0.8. So pi 0 into 0.8 will give you Pa0. That is total pressure, you know. So partial pressure of A initial Pa0 will get from this. And Pa0 by RT is Ca0. So 0.8 into 1 divided by this value of R 0.08206 at 100 degrees Celsius converted to Kelvins 100 plus 273, and this value calculated as 0.0261 moles per liter. So the given data is tabulated here. This is data, time in seconds, and partial pressure Pa in atmosphere. So from 0 seconds to 420 seconds, this is the data. We can find out conversion from this. XA is equal to 1 minus Ca by Ca0. It is same as 1 minus Pa by Pa0. So you know Pa0 is 1. So all values of Pa will give you these values of conversion. Then minus ln of 1 minus Xa. So kinetics is not known. So first we will test it for first order. If it is not fitting, then we can go for second order and so on. So we'll start with try with simple first order here. If you see the problem statement, data is given, the decomposition of reactant A in a constant volume batch reactor, the stoichiometry is given, 2A gives R plus S, and about the kinetics we don't know anything. So from this data we have to try to determine the rate law. So we'll try first order. So for first order integral method of analysis, what it suggests, you plot minus ln of 1 minus Xa as a function of time t. So minus ln of 1 minus Xa is equal to Kt. This is batch reactor data, so we use batch reactor equation. And if this fits by straight line fit through origin, it is y is equal to mx form. Y is equal to mx. If the data fits well with little bit of plus minus error, the slope will give you k. Now you can see here there is some plus minus error, but still the data is fitting well, and y is equal to mx. So m slope is 0.0096. So data is fitting with the first order assumption, first order integrated form. That means it is certainly a first order reaction. So k is 0.0096 second inverse. Once again you can see here 2A gives R plus S. So this stoichiometric coefficient, though it is 2, it is not telling us, till it is clearly mentioned that it is an elementary reaction, we cannot consider it to be second order. It order can be anything. So we have tested it for first order. Luckily, it is valid, the data is consistent with the first order. Else we have to test for second order and so on, that we have done earlier for first order, second order, and many times we have found that it has a second order fit by integral method of analysis. If it is not either first order, zero order, or second order with integral method of analysis, that means the order is not 0, 1 or 2. Then you have to go for other trials, and most of the time then we will opt for differential method of analysis. For given concentration time data, you can find out the slopes at different values of Ca, that will give you minus Ra versus Ca data, and from that, using ln of minus Ra is equal to ln of k plus n ln of Ca. So plot in y is equal to mx plus c form, and whatever n and k be obtained, we have seen that many times, that can be used accordingly. Okay. For this data also you would have tried that, still it works. So it is not, there is not that you have to use your judgment which will give you easy solution. You have options to choose from different method of analysis we have studied so far. So K is determined now. What is V0? Volumetric rate, Fa0 by Ca0. Fa0 is given. It is 100 moles of A per hour. Ca0 is determined 0.0261 moles per liter. Okay, so this value is in liters per hour. K is in second inverse, rate constant. So naturally we will convert this into per second. So this divided by 3600, 1.063 liter per second. Now we have minus ln of 1 minus x is k into t. Now we are using this for plug flow reactor. Batch reactor data, we have determined k, rate constant, same reaction. So rate law will not change, rate constant will not change. Now we are applying it to plug flow reactor because we are supposed to find the volume of plug flow reactor. So T is will be replaced by tau, and tau is nothing but V by V0. And for 95% conversion, this is 3 minus ln of 1 minus 0.95 is 3. We want volume. So volume is nothing but this 3 into V0 divided by K. 3 into V0 divided by K. V0 1.063 liter per second. This is in second inverse. Okay. So finally, what we get is volume in liters 332.12 liters for plug flow reactor.